Hello everybody, I am Abril Sahade. I am a PhD student at the Universidad Nacional of Córdoba and I work in the IATE. This work was developed with Mariana Cesare, Andrea Costa and Eve Cremades. It is about the polarity relevance in interactions between flagstrops and coronal holes. Well, my PhD thesis is about the deflection of coronal mass ejections that are eruptive events that release plasma from the solar surface to the interplanetary medium. It is important to determine the direction of propagation of those structures because they can have an encounter with Earth and produce a geomagnetic storm. Well, one of the magnetic structures in the corona capable of deviate them are coronal holes that are regions of open magnetic field lines, and they act as magnetic walls, deflecting away the CME. We consider that the sub-region of CMEs are the magnetic flagstrops, usually associated with prominences, for example, as is shown in this image. With prominences being chromospheric material that rise above the solar surface. Well, we perform numerical simulations where we simulate a magnetic flagstrop and a coronal hole. And considering that the flagstrop is very large, um, and then we perform 2.5D simulations, considering that the z-axis is the axis of symmetry. We notice that in the initial time, a null point is formed because of the cancellation of the magnetic field of the flagstrop and the coronal hole. And this null point will be very important in the evolution. When the coronal hole and the flagstrop are aligned, meaning that the foot point of the flagstrop is the same polarity of the coronal hole, then a null point will be formed in the other side of the flagstrop. While when the polarity is anti-aligned, then the coronal hole polarity is the opposite of the nearest foot point. This magnetic null point will be formed between the flagstrop and the coronal hole. So then we perform several simulations, changes the coronal hole parameters, and we study particularly the aligned and anti-aligned configurations. The left panels show the aligned configuration and the right panel shows the anti-aligned. As those cases are equivalent as well as those ones, we will just perform the simulations changing the coronal hole polarity and fixing the polarity of the flagstrop. Well, there is an example of one of those cases that we simulate. We have the star that represent the initial flagstrop position. The arrows represent the initial magnetic force over the flagstrop. The dots are the initial position of the magnetic null points, and in purple is the trajectory. So we see that the aligned trajectory goes towards the null point and after continue the path. And in the case of the anti-aligned configuration, we have that the flagstrop also is firstly attracted by the null point, continue its travel, and afterwards it deflected away of the coronal hole. We determine that the physical mechanism in both cases is the same. And it is because the magnetic force is the principal responsible of the evolution of those structures. So, well, the flagstrop is firstly attracted by the null point of energy. And after it surpasses that null point and continue the trajectory because of inertia. In the case of anti-aligned simulations, this happened until the magnetic force exerted by the bended coronal hole field lines pushes the flagstrop back. For both cases, the anti-aligned and the aligned, the final flagstrop is the one of the least resistance. So here in the GIF we can show how we can see how the flag stroke evolves towards the coronal hole and after is pushed back. So, well, at high altitudes in the corona, both cases, the aligned and the anti-aligned, will go against the coronal hole structure. So it's in concordance with the observations. Well, I mentioned that coronal hole usually acts as magnetic walls and deflects away the CMEs, but there are some observational studies that show the opposite. The opposite. Well, so we found one case that also happened that, as we see in the GIF, the prominence material first go goes towards the coronal hole, and after it deflects away of it. So as it is a projection in the plane of the sky, we decide to study the 3D evolution, and we do this with the type pointing reconstruction. For that, we take the images from stereo A and stereo B, and we determine the real 3D position through this method. And also, we analyze with the potential field surface model. We determine the magnetic field that is in the region of the ejection. Well, we decide to take many points of the ejection to really represent its evolution. We use a 304 filter and the coronagraphs. And we after reconstruct the trajectory and the magnetic field lines, the open magnetic field lines, and we saw that effectively the prominence go towards the magnetic field line. I mean, it goes towards the coronal hole and after go in the opposite direction. So we decide to consider about other possible magnetic structures that cause this effect. We analyze all the structures that appear at the source region, at the altitude of the source region. Well, we have many active regions, but in fact they are very far away of the initial position of the prominence. And we have some low energy regions over here and here, also between the initial position of the flag stroke and the coronal hole. Well, we can see that the coronal hole is the nearest magnetic structure. It could seem that this structure is at the same distance, but in fact is a projection and it is almost twice far away than this. Well, here we have the starting position. Here is the closest position to the coronal hole, and this is the final position that we can measure. That is very close to the heliospheric energy. That is a very low energy place. As because of the position of the prominence, we will not able to determine if it's anti-aligned with the coronal hole. So we decide to perform a simulation to test if this explanation is possible. Well, in this plot, we have in solid line our simulation, and the dots are the measurements. We see a very good match between both cases for the longitudinal deflection. As you can see, the latitudinal one is practically neglected. Here we have the synthetic emission of our simulation in the both filters that we can see the events. Well, our conclusions. We simulate and analyze an event that evolves towards a coronal hole in its early evolution. We came to the following conclusions. Well, first is that the aligned configurations produce deflection moving away from coronal holes, and the anti-aligned configuration firstly deflects towards the coronal hole and afterwards against it, meaning that in the later evolution stage, both cases evolve against the coronal hole as regards to the literature. Well, the mechanism deflection is the same for both cases. The flag stroke is firstly attracted by the null point, and afterwards it continues this evolution, trying to follow the least resistance path. And well, the event, the observational event that we found could be explained by the anti-aligned configuration. And as we will not able to prove that, we can just show this. Well, thank you for your attention. Uh, that's all.